Effects of external conditions. Use and disuse, combined with natural selection, organs of flight and of vision. Acclimatization. Correlation of growth. Compensation and economy of growth. False correlations. Multiple, rudimentary, and lowly organized structures variable. Parts developed in an unusual manner are highly variable, specific characters more variable than generic, secondary sexual characters variable. Species of the same genus vary in an analogous manner. Reversions to long-lost characters. Summary. I have hitherto sometimes spoken as if the variations so common and multiform in organic beings under domestication, and in a lesser degree in those in a state of nature, had been due to chance. This, of course, is a wholly incorrect expression, but it serves to acknowledge plainly our ignorance of the cause of each particular variation. Some authors believe it to be as much the function of the reproductive system to produce individual differences, or very slight deviations of structure, as to make the child like its parents. But the much greater variability, as well as the greater frequency of monstrosities, under domestication or cultivation, than under nature, leads me to believe that deviations of structure are in some way due to the nature of the conditions of life, to which the parents and their more remote ancestors have been exposed during several generations. I have remarked in the first chapter, but a long catalogue of facts which cannot be here given would be necessary to show the truth of the remark, that the reproductive system is eminently susceptible to changes in the conditions of life, and to this system being functionally disturbed in the parents, I chiefly attribute the varying or plastic condition of the offspring. The male and female sexual elements seem to be affected before that union takes place which is to form a new being. In the case of sporting plants, the bud, which in its earliest condition does not apparently differ essentially from an ovule, is alone affected. But why? Because the reproductive system is disturbed, this or that part should vary more or less, we are profoundly ignorant. Nevertheless, we can here and there dimly catch a faint ray of light, and we may feel sure that there must be some cause for each deviation of structure, however slight. How much direct effect difference of climate, food, etc., produces on any being is extremely doubtful. My impression is that the effect is extremely small in the case of animals, but perhaps rather more in that of plants. We may, at least, safely conclude that such influences cannot have produced the many striking and complex coadaptations of structure between one organic being and another, which we see everywhere throughout nature. Some little influence may be attributed to climate, food, etc. Thus, E. Forbes speaks confidently that shells at their southern limit, and when living in shallow water, are more brightly colored than those of the same species further north or from greater depths. Gould believes that birds of the same species are more brightly colored under a clear atmosphere than when living on islands or near the coast. So with insects, Wollaston is convinced that residence near the sea affects their colors. Moquin Tandon gives a list of plants which when growing near the seashore have their leaves in some degree fleshy, though not elsewhere fleshy. Several other such cases could be given. The fact of varieties of one species, when they range into the zone of habitation of other species, often acquiring in a very slight degree some of the characters of such species, accords with our view that species of all kinds are only well-marked and permanent varieties. Thus the species of shells which are confined to tropical and shallow seas are generally brighter colored than those confined to cold and deeper seas. The birds which are confined to continents are, according to Mr. Gould, brighter colored than those of islands. The insect species confined to seacoasts, as every collector knows, are often brassy or lurid. Plants which live exclusively on the seaside are very apt to have fleshy leaves. He who believes in the creation of each species will have to say that this shell, for instance, was created with bright colors for a warm sea, but that this other shell became bright colored by variation when it ranged into warmer or shallower waters. When a variation is of the slightest use to a being, we cannot tell how much of it to attribute to the accumulative action of natural selection, and how much to the conditions of life. Thus, it is well known to furriers that animals of the same species have thicker and better fur the more severe the climate is under which they have lived, but who can tell how much of this difference may be due to the warmest clad individuals having been favored and preserved during many generations, and how much to the direct action of the severe climate? For it would appear that climate has some direct action on the hair of our domestic quadrupeds. Instances could be given of the same variety being produced under conditions of life as different as can well be conceived, and, on the other hand, of different varieties being produced from the same species under the same conditions. Such facts show how indirectly the conditions of life must act. Again, innumerable instances are known to every naturalist of species keeping true, or not varying at all, although living under the most opposite climates. Such considerations as these incline me to lay very little weight on the direct action of the conditions of life. Indirectly, as already remarked, they seem to play an important part in affecting the reproductive system, and in thus inducing variability, and natural selection will then accumulate all profitable variations, however slight, until they become plainly developed and appreciable by us. Effects of use and disuse. From the facts alluded to in the first chapter, I think there can be little doubt that use in our domestic animals strengthens and enlarges certain parts, and disuse diminishes them, and that such modifications are inherited. Under free nature, we can have no standard of comparison by which to judge of the effects of long-continued use or disuse, for we know not the parent forms, but many animals have structures which can be explained by the effects of disuse. As Professor Owen has remarked, there is no greater anomaly in nature than a bird that cannot fly, yet there are several in this state. The logger-headed duck of South America can only flap along the surface of the water, and has its wings in nearly the same condition as the domestic Aylesbury duck. As the larger ground-feeding birds seldom take flight except to escape danger, I believe that the nearly wingless condition of several birds, which now inhabit or have lately inhabited several oceanic islands, tenanted by no beast of prey, has been caused by disuse. The ostrich indeed inhabits continents and is exposed to danger from which it cannot escape by flight, but by kicking it can defend itself from enemies, as well as any of the smaller quadrupeds. We may imagine that the early progenitor of the ostrich had habits like those of a bustard, and that as natural selection increased in successive generations the size and weight of its body, its legs were used more, and its wings less, until they became incapable of flight. Kirby has remarked, and I have observed the same fact, that the anterior tarsi, or feet, of many male dung-feeding beetles are very often broken off. He examined 17 specimens in his own collection, and not one had even a relic left. In the Onyx apelles the tarsi are so habitually lost, that the insect has been described as not having them. In some other genera they are present, but in a rudimentary condition. In the Atuchus or sacred beetle of the Egyptians, they are totally deficient. There is not sufficient evidence to induce us to believe that mutilations are ever inherited, and I should prefer explaining the entire absence of the anterior tarsi in Atuchus, and their rudimentary condition in some other genera, by the long-continued effects of disuse in their progenitors, for as the tarsi are almost always lost in many dung-feeding beetles, they must be lost early in life, and therefore cannot be much used by these insects. In some cases we might easily put down to disuse modifications of structure which are wholly, or mainly, due to natural selection. Mr. Wollaston has discovered the remarkable fact that 200 beetles, out of the 550 species inhabiting Madeira, are so far deficient in wings that they cannot fly, and that of the 29 endemic genera, no less than 23 genera have all their species in this condition. Several facts, namely, that beetles in many parts of the world are very frequently blown to sea and perish, that the beetles in Madeira, as observed by Mr. Wollaston, lie much concealed until the wind lulls and the sun shines, that the proportion of wingless beetles is larger on the exposed desertas than in Madeira itself, and especially the extraordinary fact, so strongly insisted on by Mr. Wollaston, of the almost entire absence of certain large groups of beetles, elsewhere excessively numerous, and which groups have habits of life almost necessitating frequent flight. These several considerations have made me believe that the wingless condition of so many Madeira beetles is mainly due to the action of natural selection, but combined probably with disuse. For during thousands of successive generations each individual beetle which flew least, either from its wings having been ever so little less perfectly developed or from indolent habit, will have had the best chance of surviving from not being blown out to sea, and, on the other hand, those beetles which most readily took to flight will oftenest have been blown to sea and thus have been destroyed. The insects in Madeira which are not ground feeders, and which, as the flower-feeding Coleoptera and Lepidoptera, must habitually use their wings to gain their subsistence, have, as Mr. Wollaston suspects, their wings not at all reduced, but even enlarged. This is quite compatible with the action of natural selection. For when a new insect first arrived on the island, the tendency of natural selection to enlarge or to reduce the wings would depend on whether a greater number of individuals were saved by successfully battling with the winds, or by giving up the attempt and rarely or never flying. As with mariners shipwrecked near a coast, it would have been better for the good swimmers if they had been able to swim still further, whereas it would have been better for the bad swimmers if they had not been able to swim at all and had stuck to the wreck. The eyes of moles and of some burrowing rodents are rudimentary in size, and in some cases are quite covered up by skin and fur. This state of the eyes is probably due to gradual reduction from disuse, but aided perhaps by natural selection. In South America, a burrowing rodent, the tucutuco, or tenemes, is even more subterranean in its habits than the mole, and I was assured by a Spaniard, who had often caught them, that they were frequently blind. One which I kept alive was certainly in this condition, the cause, as appeared on dissection, having been inflammation of the nictitating membrane. As frequent inflammation of the eyes must be injurious to any animal, and as eyes are certainly not indispensable to animals with subterranean habits, a reduction in their size with the adhesion of the eyelids and growth of fur over them might in such case be an advantage, and if so, natural selection would constantly aid the effects of disuse. It is well known that several animals, belonging to the most different classes, which inhabit the caves of Styria and of Kentucky, are blind. In some of the crabs the footstalk for the eye remains, though the eye is gone. The stand for the telescope is there, though the telescope with its glasses has been lost. As it is difficult to imagine that eyes, though useless, could be in any way injurious to animals living in darkness, I attribute their loss wholly to disuse. In one of the blind animals, namely, the cave rat, the eyes are of immense size, and Professor Silliman thought that it regained, after living some days in the light, some slight power of vision. In the same manner as in Madeira, the wings of some of the insects have been enlarged, and the wings of others have been reduced by natural selection aided by use and disuse, so in the case of the cave rat natural selection seems to have struggled with the loss of light and to have increased the size of the eyes, whereas with all the other inhabitants of the caves, disuse by itself seems to have done its work. It is difficult to imagine conditions of life more similar than deep limestone caverns under a nearly similar climate, so that on the common view of the blind animals having been separately created for the American and European caverns, close similarity in their organization and affinities might have been expected, but, as Skyett and others have remarked, this is not the case, and the cave insects of the two continents are not more closely allied than might have been anticipated from the general resemblance of the other inhabitants of North America and Europe. On my view, we must suppose that American animals, having ordinary powers of vision, slowly migrated by successive generations from the outer world into the deeper and deeper recesses of the Kentucky caves, as did European animals into the caves of Europe. We have some evidence of this gradation of habit, for, as Skyett remarks, animals not far remote from ordinary forms prepare the transition from light to darkness. Next follow those that are constructed for twilight, and, last of all, those destined for total darkness. By the time that an animal had reached, after numberless generations, the deepest recesses, disuse will on this view have more or less perfectly obliterated its eyes, and natural selection will often have effected other changes, such as an increase in the length of the antennae or palpi, as a compensation for blindness. Notwithstanding such modifications, we might expect still to see in the cave animals of America affinities to the other inhabitants of that continent, and in those of Europe, to the inhabitants of the European continent. And this is the case with some of the American cave animals, as I hear from Professor Dana, and some of the European cave insects are very closely allied to those of the surrounding country. It would be most difficult to give any rational explanation of the affinities of the blind cave animals to the other inhabitants of the two continents on the ordinary view of their independent creation. That several of the inhabitants of the caves of the Old and New Worlds should be closely related, we might expect from the well-known relationship of most of their other productions. Far from feeling any surprise that some of the cave animals should be very anomalous, as Agassiz has remarked in regard to the blind fish, the Amblyopsis, and as is the case with the blind Proteus with reference to the reptiles of Europe, I am only surprised that more wrecks of ancient life have not been preserved, owing to the less severe competition to which the inhabitants of these dark abodes will probably have been exposed. Acclimatization. Habit is hereditary with plants, as in the period of flowering, in the amount of rain requisite for seeds to germinate, in the time of sleep, etc., and this leads me to say a few words on acclimatization. As it is extremely common for species of the same genus to inhabit very hot and very cold countries, and as I believe that all the species of the same genus have descended from a single parent, if this view be correct, acclimatization must be readily effected during long-continued descent. It is notorious that each species is adapted to the climate of its own home. Species from an Arctic or even from a temperate region cannot endure a tropical climate, or conversely. So again, many succulent plants cannot endure a damp climate. But the degree of adaptation of species to the climates under which they live is often overrated. We may infer this from our frequent inability to predict whether or not an imported plant will endure our climate, and from the number of plants and animals brought from warmer countries which here enjoy good health. We have reason to believe that species in a state of nature are limited in their ranges by the competition of other organic beings quite as much as, or more than, by adaptation to particular climates. But whether or not the adaptation be generally very close, we have evidence, in the case of some few plants, of their becoming, to a certain extent, naturally habituated to different temperatures, or becoming acclimatized. Thus the pines and rhododendrons, raised from seed collected by Dr. Hooker from trees growing at different heights on the Himalaya, were found in this country to possess different constitutional powers of resisting cold. Mr. Thwaites informs me that he has observed similar facts in Ceylon, and analogous observations have been made by Mr. H.C. Watson on European species of plants brought from the Azores to England. In regard to animals, several authentic cases could be given of species within historical times having largely extended their range from warmer to cooler latitudes, and conversely, but we do not positively know that these animals were strictly adapted to their native climate, but in all ordinary cases we assume such to be the case, nor do we know that they have subsequently become acclimatized to their new homes. As I believe that our domestic animals were originally chosen by uncivilized man because they were useful and bred readily under confinement, and not because they were subsequently found capable of far extended transportation, I think the common and extraordinary capacity in our domestic animals of not only withstanding the most different climates but of being perfectly fertile, a far severer test, under them, may be used as an argument that a large proportion of other animals, now in a state of nature, could easily be brought to bear widely different climates. We must not, however, push the foregoing argument too far, on account of the probable origin of some of our domestic animals from several wild stocks. The blood, for instance, of a tropical and Arctic wolf or wild dog may perhaps be mingled in our domestic breeds. The rat and mouse cannot be considered as domestic animals, but they have been transported by man to many parts of the world, and now have a far wider range than any other rodent, living free under the cold climate of Faroe in the north and of the Falklands in the south, and on many islands in the torrid zones. Hence I am inclined to look at adaptation to any special climate as a quality readily grafted on an innate wide flexibility of constitution, which is common to most animals. On this view, the capacity of enduring the most different climates by man himself and by his domestic animals, and such facts as that former species of the elephant and rhinoceros were capable of enduring a glacial climate, whereas the living species are now all tropical or subtropical in their habits, ought not to be looked at as anomalies, but merely as examples of a very common flexibility of constitution, brought, under peculiar circumstances, into play. How much of the acclimatization of species to any peculiar climate is due to mere habit, and how much to the natural selection of varieties having different innate constitutions, and how much to both means combined, is a very obscure question. That habit or custom has some influence, I must believe, both from analogy, and from the incessant advice given in agricultural works, even in the ancient encyclopedias of China, to be very cautious in transposing animals from one district to another, for it is not likely that man should have succeeded in selecting so many breeds and subbreeds with constitutions specially fitted for their own districts. The result must, I think, be due to habit. On the other hand, I can see no reason to doubt that natural selection will continually tend to preserve those individuals which are born with constitutions best adapted to their native countries. In treatises on many kinds of cultivated plants, certain varieties are said to withstand certain climates better than others. This is very strikingly shown in works on fruit trees published in the United States, in which certain varieties are habitually recommended for the northern, and others for the southern states, and as most of these varieties are of recent origin, they cannot owe their constitutional differences to habit. The case of the Jerusalem artichoke, which is never propagated by seed, and of which consequently new varieties have not been produced, has even been advanced, for it is now as tender as ever it was, as proving that acclimatization cannot be effected. The case, also, of the kidney bean has been often cited for a similar purpose, and with much greater weight, but until someone will sow, during a score of generations, his kidney beans so early that a very large proportion are destroyed by frost, and then collect seed from the few survivors, with care to prevent accidental crosses, and then again get seed from these seedlings, with the same precautions, the experiment cannot be said to have been even tried. Nor let it be supposed that no differences in the constitution of seedling kidney beans ever appear, for an account has been published how much more hardy some seedlings appeared to be than others. On the whole, I think we may conclude that habit, use, and disuse have, in some cases, played a considerable part in the modification of the constitution, and of the structure of various organs, but that the effects of use and disuse have often been largely combined with, and sometimes overmastered by, the natural selection of innate differences. Correlation of growth. I mean by this expression that the whole organization is so tied together during its growth and development, that when slight variations in any one part occur, and are accumulated through natural selection, other parts become modified. This is a very important subject, most imperfectly understood. The most obvious case is that modifications accumulated solely for the good of the young or larva will, it may safely be concluded, affect the structure of the adult, in the same manner as any malconformation affecting the early embryo seriously affects the whole organization of the adult. The several parts of the body which are homologous, and which, at an early embryonic period, are alike, seem liable to vary in an allied manner. We see this in the right and left sides of the body varying in the same manner, in the front and hind legs, and even in the jaws and limbs, varying together, for the lower jaw is believed to be homologous with the limbs. These tendencies, I do not doubt, may be mastered more or less completely by natural selection. Thus a family of stags once existed with an antler only on one side, and if this had been of any great use to the breed it might probably have been rendered permanent by natural selection. Homologous parts, as has been remarked by some authors, tend to cohere. This is often seen in monstrous plants, and nothing is more common than the union of homologous parts in normal structures, as the union of the petals of the corolla into a tube. Hard parts seem to affect the form of adjoining soft parts. It is believed by some authors that the diversity in the shape of the pelvis in birds causes the remarkable diversity in the shape of their kidneys. Others believe that the shape of the pelvis in the human mother influences by pressure the shape of the head of the child. In snakes, according to Schlegel, the shape of the body and the manner of swallowing determine the position of several of the most important viscera. The nature of the bond of correlation is very frequently quite obscure. Geoffrey St. Hilaire has forcibly remarked that certain malconformations very frequently, and that others rarely coexist, without our being able to assign any reason. What can be more singular than the relation between blue eyes and deafness in cats, and the tortoiseshell color with the female sex, the feathered feet and skin between the outer toes in pigeons, and the presence of more or less down on the young birds when first hatched, with the future color of their plumage, or, again, the relation between the hair and teeth in the naked Turkish dog, though here probably homology comes into play? With respect to this latter case of correlation, I think it can hardly be accidental that if we pick out the two orders of Mammalia which are most abnormal in their dermal coverings, viz. Cetacea, whales, Anidentata, armadillos, scaly anteaters, etc., that these are likewise the most abnormal in their teeth. I know of no case better adapted to show the importance of the laws of correlation in modifying important structures, independently of utility and, therefore, of natural selection, than that of the difference between the outer and inner flowers in some compositous and umbelliferous plants. Everyone knows the difference in the ray and central florets of, for instance, the daisy, and this difference is often accompanied with the abortion of parts of the flower. But, in some compositous plants, the seeds also differ in shape and sculpture, and even the ovary itself, with its accessory parts, differs, as has been described by Cassini. These differences have been attributed by some authors to pressure, and the shape of the seeds in the ray florets in some compositae countenances this idea, but, in the case of the corolla of the umbelliferae, it is by no means, as Dr. Hooker informs me, in species with the densest heads that the inner and outer flowers most frequently differ. It might have been thought that the development of the ray petals by drawing nourishment from certain other parts of the flower had caused their abortion, but in some compositae there is a difference in the seeds of the outer and inner florets without any difference in the corolla. Possibly, these several differences may be connected with some difference in the flow of nutriment towards the central and external flowers. We know, at least, that in irregular flowers, those nearest to the axis are oftenest subject to poloria, and become regular. I may add, as an instance of this, and of a striking case of correlation, that I have recently observed in some garden pelargoniums, that the central flower of the truss often loses the patches of darker color in the two upper petals, and that when this occurs, the adherent nectary is quite aborted. When the color is absent from only one of the two upper petals, the nectary is only much shortened. With respect to the difference in the corolla of the central and exterior flowers of a head or umbel, I do not feel at all sure that C. Sprengdel's idea that the ray florets serve to attract insects, whose agency is highly advantageous in the fertilization of plants of these two orders, is so far-fetched, as it may at first appear, and if it be advantageous, natural selection may have come into play. But in regard to the differences both in the internal and external structure of the seeds, which are not always correlated with any differences in the flowers, it seems impossible that they can be in any way advantageous to the plant, yet in the umbelliferae these differences are of such apparent importance, the seeds being in some cases, according to Tausch, orthospermous in the exterior flowers and coelospermous in the central flowers, that the elder de Candolle founded his main divisions of the order on analogous differences. Hence we see that modifications of structure, viewed by systematists as of high value, may be wholly due to unknown laws of correlated growth, and without being, as far as we can see, of the slightest service to the species. We may often falsely attribute to correlation of growth structures which are common to whole groups of species, and which in truth are simply due to inheritance, for an ancient progenitor may have acquired through natural selection some one modification in structure, and, after thousands of generations, some other and independent modification, and these two modifications, having been transmitted to a whole group of descendants with diverse habits, would naturally be thought to be correlated in some necessary manner. So, again, I do not doubt that some apparent correlations, occurring throughout whole orders, are entirely due to the manner alone in which natural selection can act. For instance, Alf. de Candolle has remarked that winged seeds are never found in fruits which do not open. I should explain the rule by the fact that seeds could not gradually become winged through natural selection, except in fruits which opened, so that the individual plants producing seeds which were a little better fitted to be wafted further, might get an advantage over those producing seed less fitted for dispersal, and this process could not possibly go on in fruit which did not open. The elder Geoffrey and Goethe propounded, at about the same period, their law of compensation or balancement of growth, or, as Goethe expressed it, in order to spend on one side, nature is forced to economize on the other side. I think this holds true to a certain extent with our domestic productions. If nourishment flows to one part or organ in excess, it rarely flows, at least in excess, to another part, thus it is difficult to get a cow to give much milk and to fatten readily. The same varieties of the cabbage do not yield abundant and nutritious foliage and a copious supply of oil-bearing seeds. When the seeds in our fruits become atrophied, the fruit itself gains largely in size and quality. In our poultry, a large tuft of feathers on the head is generally accompanied by a diminished comb, and a large beard by diminished wattles. With species in a state of nature, it can hardly be maintained that the law is of universal application, but many good observers, more especially botanists, believe in its truth. I will not, however, here give any instances, for I see hardly any way of distinguishing between the effects, on the one hand, of a part being largely developed through natural selection and another an adjoining part being reduced by the same process or by disuse, and, on the other hand, the actual withdrawal of nutriment from one part owing to the excess of growth in another an adjoining part. I suspect, also, that some of the cases of compensation which have been advanced, and likewise some other facts, may be merged under a more general principle, namely, that natural selection is continually trying to economize in every part of the organization. If under changed conditions of life a structure before useful becomes less useful, any diminution, however slight, in its development, will be seized on by natural selection, for it will profit the individual not to have its nutriment wasted in building up an useless structure. I can thus only understand a fact with which I was much struck when examining cirripedes, and of which many other instances could be given, namely, that when a cirripede is parasitic within another and is thus protected, it loses more or less completely its own shell or carapace. This is the case with the male Ibla, and in a truly extraordinary manner with the Proteolepis, for the carapace in all other cirripedes consists of the three highly important anterior segments of the head enormously developed, and furnished with great nerves and muscles, but in the parasitic and protected Proteolepis, the whole anterior part of the head is reduced to the merest rudiment attached to the bases of the prehensile antennae. Now the saving of a large and complex structure, when rendered superfluous by the parasitic habits of the Proteolepis, though effected by slow steps, would be a decided advantage to each successive individual of the species, for in the struggle for life to which every animal is exposed, each individual Proteolepis would have a better chance of supporting itself, by less nutriment being wasted in developing a structure now become useless. Thus, as I believe, natural selection will always succeed in the long run in reducing and saving every part of the organization, as soon as it is rendered superfluous, without by any means causing some other part to be largely developed in a corresponding degree. And, conversely, that natural selection may perfectly well succeed in largely developing any organ, without requiring as a necessary compensation the reduction of some adjoining part. It seems to be a rule, as remarked by is. Geoffrey St. Hilaire, both in varieties and in species, that when any part or organ is repeated many times in the structure of the same individual, as the vertebrae in snakes, and the stamens in polyandrous flowers, the number is variable, whereas the number of the same part or organ, when it occurs in lesser numbers, is constant. The same author and some botanists have further remarked that multiple parts are also very liable to variation in structure. Inasmuch as this vegetative repetition, to use Professor Owen's expression, seems to be a sign of low organization, the foregoing remark seems connected with the very general opinion of naturalists, that beings low in the scale of nature are more variable than those which are higher. I presume that lowness in this case means that the several parts of the organization have been but little specialized for particular functions, and as long as the same part has to perform diversified work, we can perhaps see why it should remain variable, that is, why natural selection should have preserved or rejected each little deviation of form less carefully than when the part has to serve for one special purpose alone. In the same way that a knife which has to cut all sorts of things may be of almost any shape, whilst a tool for some particular object had better be of some particular shape. Natural selection, it should never be forgotten, can act on each part of each being, solely through and for its advantage. Rudimentary parts, it has been stated by some authors, and I believe with truth, are apt to be highly variable. We shall have to recur to the general subject of rudimentary and aborted organs, and I will here only add that their variability seems to be owing to their uselessness, and therefore to natural selection having no power to check deviations in their structure. Thus, rudimentary parts are left to the free play of the various laws of growth, to the effects of long-continued disuse, and to the tendency to reversion. A part developed in any species in an extraordinary degree or manner, in comparison with the same part in allied species, tends to be highly variable. Several years ago I was much struck with a remark, nearly to the above effect, published by Mr. Waterhouse. I infer also from an observation made by Professor Owen, with respect to the length of the arms of the orangutan, that he has come to a nearly similar conclusion. It is hopeless to attempt to convince anyone of the truth of this proposition without giving the long array of facts which I have collected, and which cannot possibly be here introduced. I can only state my conviction that it is a rule of high generality. I am aware of several causes of error, but I hope that I have made due allowance for them. It should be understood that the rule by no means applies to any part, however unusually developed, unless it be unusually developed in comparison with the same part in closely allied species. Thus, the bat's wing is a most abnormal structure in the class Mammalia, but the rule would not here apply, because there is a whole group of bats having wings. It would apply only if some one species of bat had its wings developed in some remarkable manner in comparison with the other species of the same genus. The rule applies very strongly in the case of secondary sexual characters, when displayed in any unusual manner. The term secondary sexual characters, used by Hunter, applies to characters which are attached to one sex, but are not directly connected with the act of reproduction. The rule applies to males and females, but as females more rarely offer remarkable secondary sexual characters, it applies more rarely to them. The rule being so plainly applicable in the case of secondary sexual characters, may be due to the great variability of these characters, whether or not displayed in any unusual manner, of which fact I think there can be little doubt. But that our rule is not confined to secondary sexual characters is clearly shown in the case of hermaphrodite cirripedes, and I may here add, that I particularly attended to Mr. Waterhouse's remark, whilst investigating this order, and I am fully convinced that the rule almost invariably holds good with cirripedes. I shall, in my future work, give a list of the more remarkable cases. I will here only briefly give one, as it illustrates the rule in its largest application. The opercular valves of sessile cirripedes, rock barnacles, are, in every sense of the word, very important structures, and they differ extremely little even in different genera, but in the several species of one genus, Pergoma, these valves present a marvelous amount of diversification, the homologous valves in the different species being sometimes wholly unlike in shape, and the amount of variation in the individuals of several of the species is so great, that it is no exaggeration to state that the varieties differ more from each other in the characters of these important valves than do other species of distinct genera. As birds within the same country vary in a remarkably small degree, I have particularly attended to them, and the rule seems to me certainly to hold good in this class. I cannot make out that it applies to plants, and this would seriously have shaken my belief in its truth, had not the great variability in plants made it particularly difficult to compare their relative degrees of variability. When we see any part or organ developed in a remarkable degree or manner in any species, the fair presumption is that it is of high importance to that species. Nevertheless, the part in this case is eminently liable to variation. Why should this be so? On the view that each species has been independently created, with all its parts as we now see them, I can see no explanation. But on the view that groups of species have descended from other species, and have been modified through natural selection, I think we can obtain some light. In our domestic animals, if any part, or the whole animal, be neglected and no selection be applied, that part, for instance, the comb and the dorking fowl, or the whole breed will cease to have a nearly uniform character. The breed will then be said to have degenerated. In rudimentary organs, and in those which have been but little specialized for any particular purpose, and perhaps in polymorphic groups, we see a nearly parallel natural case, for in such cases natural selection either has not or cannot come into full play, and thus the organization is left in a fluctuating condition. But what here more especially concerns us is that in our domestic animals those points, which at the present time are undergoing rapid change by continued selection, are also eminently liable to variation. Look at the breeds of the pigeon, see what a prodigious amount of difference there is in the beak of the different tumblers, in the beak and wattle of the different carriers, in the carriage and tail of our fantails, etc., these being the points now mainly attended to by English fanciers. Even in the subbreeds, as in the short-faced tumbler, it is notoriously difficult to breed them nearly to perfection, and frequently individuals are born which depart widely from the standard. There may be truly said to be a constant struggle going on between, on the one hand, the tendency to reversion to a less modified state, as well as an innate tendency to further variability of all kinds, and, on the other hand, the power of steady selection to keep the breed true. In the long run, selection gains the day, and we do not expect to fail so far as to breed a bird as coarse as a common tumbler from a good short-faced strain. But as long as selection is rapidly going on, there may always be expected to be much variability in the structure undergoing modification. It further deserves notice that these variable characters, produced by man's selection, sometimes become attached, from causes quite unknown to us, more to one sex than to the other, generally to the male sex, as with the wattle of carriers and the enlarged crop of pouters. Now let us turn to nature. When a part has been developed in an extraordinary manner in any one species, compared with the other species of the same genus, we may conclude that this part has undergone an extraordinary amount of modification, since the period when the species branched off from the common progenitor of the genus. This period will seldom be remote in any extreme degree, as species very rarely endure for more than one geological period. An extraordinary amount of modification implies an unusually large and long-continued amount of variability, which has continually been accumulated by natural selection for the benefit of the species. But as the variability of the extraordinarily developed part or organ has been so great and long continued within a period not excessively remote, we might, as a general rule, expect still to find more variability in such parts than in other parts of the organization, which have remained for a much longer period nearly constant. And this, I am convinced, is the case. That the struggle between natural selection on the one hand, and the tendency to reversion and variability on the other hand, will in the course of time cease, and that the most abnormally developed organs may be made constant, I can see no reason to doubt. Hence, when an organ, however abnormal it may be, has been transmitted in approximately the same condition to many modified descendants, as in the case of the wing of the bat, it must have existed, according to my theory, for an immense period in nearly the same state, and thus it comes to be no more variable than any other structure. It is only in those cases in which the modification has been comparatively recent and extraordinarily great that we ought to find the generative variability, as it may be called, still present in a high degree. For in this case the variability will seldom as yet have been fixed by the continued selection of the individuals varying in the required manner and degree, and by the continued rejection of those tending to revert to a former and less modified condition. The principle included in these remarks may be extended. It is notorious that specific characters are more variable than generic. To explain by a simple example what is meant. If some species in a large genus of plants had blue flowers and some had red, the color would be only a specific character, and no one would be surprised at one of the blue species varying into red, or conversely, but if all the species had blue flowers, the color would become a generic character, and its variation would be a more unusual circumstance. I have chosen this example because an explanation is not in this case applicable, which most naturalists would advance, namely, that specific characters are more variable than generic, because they are taken from parts of less physiological importance than those commonly used for classing genera. I believe this explanation is partly, yet only indirectly, true. I shall, however, have to return to this subject in our chapter on classification. It would be almost superfluous to adduce evidence in support of the above statement, that specific characters are more variable than generic, but I have repeatedly noticed in works on natural history, that when an author has remarked with surprise that some important organ or part, which is generally very constant throughout large groups of species, has differed considerably in closely allied species, that it has, also, been variable in the individuals of some of the species. And this fact shows that a character, which is generally of generic value, when it sinks in value and becomes only of specific value, often becomes variable, though its physiological importance may remain the same. Something of the same kind applies to monstrosities, at least is. Geoffrey St. Hilaire seems to entertain no doubt that the more an organ normally differs in the different species of the same group, the more subject it is to individual anomalies. On the ordinary view of each species having been independently created, why should that part of the structure, which differs from the same part in other independently created species of the same genus, be more variable than those parts which are closely alike in the several species? I do not see that any explanation can be given. But on the view of species being only strongly marked and fixed varieties, we might surely expect to find them still often continuing to vary in those parts of their structure which have varied within a moderately recent period, and which have thus come to differ. Or to state the case in another manner, the points in which all the species of a genus resemble each other, and in which they differ from the species of some other genus, are called generic characters, and these characters in common I attribute to inheritance from a common progenitor, for it can rarely have happened that natural selection will have modified several species, fitted to more or less widely different habits, in exactly the same manner, and as these so-called generic characters have been inherited from a remote period, since that period when the species first branched off from their common progenitor, and subsequently have not varied or come to differ in any degree, or only in a slight degree, it is not probable that they should vary at the present day. On the other hand, the points in which species differ from other species of the same genus are called specific characters, and as these specific characters have varied and come to differ within the period of the branching off of the species from a common progenitor, it is probable that they should still often be in some degree variable, at least more variable than those parts of the organization which have for a very long period remained constant. In connection with the present subject, I will make only two other remarks. I think it will be admitted, without my entering on details, that secondary sexual characters are very variable. I think it also will be admitted that species of the same group differ from each other more widely in their secondary sexual characters than in other parts of their organization. Compare, for instance, the amount of difference between the males of gallinaceous birds, in which secondary sexual characters are strongly displayed, with the amount of difference between their females, and the truth of this proposition will be granted. The cause of the original variability of secondary sexual characters is not manifest, but we can see why these characters should not have been rendered as constant and uniform as other parts of the organization, for secondary sexual characters have been accumulated by sexual selection, which is less rigid in its action than ordinary selection, as it does not entail death, but only gives fewer offspring to the less favored males. Whatever the cause may be of the variability of secondary sexual characters, as they are highly variable, sexual selection will have had a wide scope for action, and may thus readily have succeeded in giving to the species of the same group a greater amount of difference in their sexual characters than in other parts of their structure. It is a remarkable fact that the secondary sexual differences between the two sexes of the same species are generally displayed in the very same parts of the organization in which the different species of the same genus differ from each other. Of this fact I will give an illustration: two instances, the first which happened to stand on my list, and as the differences in these cases are of a very unusual nature, the relation can hardly be accidental. The same number of joints in the tarsi is a character generally common to very large groups of beetles, but in the Ingidae, as Westwood has remarked, the number varies greatly, and the number likewise differs in the two sexes of the same species. Again, in Fossorial Hymenoptera, the manner of narration of the wings is a character of the highest importance, because common to large groups, but in certain genera the narration differs in the different species, and likewise in the two sexes of the same species. This relation has a clear meaning on my view of the subject. I look at all the species of the same genus as having as certainly descended from the same progenitor as have the two sexes of any one of the species. Consequently, whatever part of the structure of the common progenitor, or of its early descendants, became variable, variations of this part would, it is highly probable, be taken advantage of by natural and sexual selection, in order to fit the several species to their several places in the economy of nature, and likewise to fit the two sexes of the same species to each other, or to fit the males and females to different habits of life, or the males to struggle with other males for the possession of the females. Finally, then, I conclude that the greater variability of specific characters, or those which distinguish species from species, than of generic characters, or those which the species possess in common, that the frequent extreme variability of any part which is developed in a species in an extraordinary manner in comparison with the same part in its congeners, and the not great degree of variability in a part, however extraordinarily it may be developed, if it be common to a whole group of species, that the great variability of secondary sexual characters, and the great amount of difference in these same characters between closely allied species, that secondary sexual and ordinary specific differences are generally displayed in the same parts of the organization, are all principles closely connected together. All being mainly due to the species of the same group having descended from a common progenitor, from whom they have inherited much in common, to parts which have recently and largely varied being more likely still to go on varying than parts which have long been inherited and have not varied, to natural selection having more or less completely, according to the lapse of time, overmastered the tendency to reversion and to further variability, to sexual selection being less rigid than ordinary selection, and to variations in the same parts having been accumulated by natural and sexual selection, and thus adapted for secondary sexual, and for ordinary specific purposes. Distinct species present analogous variations, and a variety of one species often assumes some of the characters of an allied species, or reverts to some of the characters of an early progenitor. These propositions will be most readily understood by looking to our domestic races. The most distinct breeds of pigeons, in countries most widely apart, present subvarieties with reversed feathers on the head and feathers on the feet, characters not possessed by the aboriginal rock pigeon. These then are analogous variations in two or more distinct races. The frequent presence of 14 or even 16 tail feathers in the pouter may be considered as a variation representing the normal structure of another race, the fantail. I presume that no one will doubt that all such analogous variations are due to the several races of the pigeon having inherited from a common parent the same constitution and tendency to variation, when acted on by similar unknown influences. In the vegetable kingdom we have a case of analogous variation in the enlarged stems, or roots as commonly called, of the Swedish turnip and rutabaga, plants which several botanists rank as varieties produced by cultivation from a common parent. If this be not so, the case will then be one of analogous variation in two so-called distinct species, and to these a third may be added, namely, the common turnip. According to the ordinary view of each species having been independently created, we should have to attribute this similarity in the enlarged stems of these three plants, not to the vera causa of community of descent, and a consequent tendency to vary in a like manner, but to three separate yet closely related acts of creation. With pigeons, however, we have another case, namely, the occasional appearance in all the breeds, of slaty blue birds with two black bars on the wings, a white rump, a bar at the end of the tail, with the outer feathers externally edged near their bases with white. As all these marks are characteristic of the parent rock pigeon, I presume that no one will doubt that this is a case of reversion, and not of a new yet analogous variation appearing in the several breeds. We may, I think, confidently come to this conclusion, because, as we have seen, these colored marks are eminently liable to appear in the crossed offspring of two distinct and differently colored breeds, and in this case there is nothing in the external conditions of life to cause the reappearance of the slaty blue, with the several marks, beyond the influence of the mere act of crossing on the laws of inheritance. No doubt it is a very surprising fact that characters should reappear after having been lost for many, perhaps for hundreds of generations. But when a breed has been crossed only once by some other breed, the offspring occasionally show a tendency to revert in character to the foreign breed for many generations, some say, for a dozen or even a score of generations. After 12 generations, the proportion of blood, to use a common expression, of any one ancestor, is only 1 in 2048, and yet, as we see, it is generally believed that a tendency to reversion is retained by this very small proportion of foreign blood. In a breed which has not been crossed, but in which both parents have lost some character which their progenitor possessed, the tendency, whether strong or weak, to reproduce the lost character might be, as was formerly remarked, for all that we can see to the contrary, transmitted for almost any number of generations. When a character which has been lost in a breed reappears after a great number of generations, the most probable hypothesis is not that the offspring suddenly takes after an ancestor some 100 generations distant, but that in each successive generation there has been a tendency to reproduce the character in question, which at last, under unknown favorable conditions, gains an ascendancy. For instance, it is probable that in each generation of the barred pigeon, which produces most rarely a blue and black barred bird, there has been a tendency in each generation in the plumage to assume this color. This view is hypothetical, but could be supported by some facts, and I can see no more abstract improbability in a tendency to produce any character being inherited for an endless number of generations, than in quite useless or rudimentary organs being, as we all know them to be, thus inherited. Indeed, we may sometimes observe a mere tendency to produce a rudiment inherited, for instance, in the common snapdragon, Antirrhinum, a rudiment of a fifth stamen so often appears, that this plant must have an inherited tendency to produce it. As all the species of the same genus are supposed, on my theory, to have descended from a common parent, it might be expected that they would occasionally vary in an analogous manner, so that a variety of one species would resemble in some of its characters another species, this other species being on my view only a well-marked and permanent variety. But characters thus gained would probably be of an unimportant nature, for the presence of all important characters will be governed by natural selection, in accordance with the diverse habits of the species, and will not be left to the mutual action of the conditions of life and of a similar inherited constitution. It might further be expected that the species of the same genus would occasionally exhibit reversions to lost ancestral characters. As, however, we never know the exact character of the common ancestor of a group, we could not distinguish these two cases. If, for instance, we did not know that the rock pigeon was not feather-footed or turn-crowned, we could not have told whether these characters in our domestic breeds were reversions or only analogous variations, but we might have inferred that the blueness was a case of reversion, from the number of the markings, which are correlated with the blue tint, and which it does not appear probable would all appear together from simple variation. More especially we might have inferred this, from the blue color and marks so often appearing when distinct breeds of diverse colors are crossed. Hence, though under nature it must generally be left doubtful what cases are reversions to an anciently existing character, and what are new but analogous variations, yet we ought, on my theory, sometimes to find the varying offspring of a species assuming characters, either from reversion or from analogous variation, which already occur in some other members of the same group. And this undoubtedly is the case in nature. A considerable part of the difficulty in recognizing a variable species in our systematic works is due to its varieties mocking, as it were, some of the other species of the same genus. A considerable catalogue, also, could be given of forms intermediate between two other forms, which themselves must be doubtfully ranked as either varieties or species, and this shows, unless all these forms be considered as independently created species, that the one in varying has assumed some of the characters of the other, so as to produce the intermediate form. But the best evidence is afforded by parts or organs of an important and uniform nature occasionally varying so as to acquire, in some degree, the character of the same part or organ in an allied species. I have collected a long list of such cases, but here, as before, I lie under a great disadvantage in not being able to give them. I can only repeat that such cases certainly do occur, and seem to me very remarkable. I will, however, give one curious and complex case, not indeed as affecting any important character, but from occurring in several species of the same genus, partly under domestication and partly under nature. It is a case apparently of reversion. The S not rarely has very distinct transverse bars on its legs, like those on the legs of a zebra. It has been asserted that these are plainest in the foal, and from inquiries which I have made, I believe this to be true. It has also been asserted that the stripe on each shoulder is sometimes double. The shoulder stripe is certainly very variable in length and outline. A white ass, but not an albino, has been described without either spinal or shoulder stripe, and these stripes are sometimes very obscure, or actually quite lost, in dark-colored asses. The colon of Pallas is said to have been seen with a double shoulder stripe. The Hemianus has no shoulder stripe, but traces of it, as stated by Mr. Blyth and others, occasionally appear, and I have been informed by Colonel Poole that the foals of this species are generally striped on the legs, and faintly on the shoulder. The quagga, though so plainly barred like a zebra over the body, is without bars on the legs, but Dr. Gray has figured one specimen with very distinct zebra-like bars on the hocks. With respect to the horse, I have collected cases in England of the spinal stripe in horses of the most distinct breeds, and of all colors. Transverse bars on the legs are not rare in duns, mouse duns, and in one instance in a chestnut, a faint shoulder stripe may sometimes be seen in duns, and I have seen a trace in a bay horse. My son made a careful examination and sketch for me of a dun Belgian cart horse with a double stripe on each shoulder and with leg stripes, and a man, whom I can implicitly trust, has examined for me a small dun Welsh pony with 3 short parallel stripes on each shoulder. In the northwest part of India, the Kathiawar breed of horses is so generally striped that, as I hear from Colonel Poole, who examined the breed for the Indian government, a horse without stripes is not considered as purely bred. The spine is always striped, the legs are generally barred, and the shoulder stripe, which is sometimes double and sometimes treble, is common. The side of the face, moreover, is sometimes striped. The stripes are plainest in the foal, and sometimes quite disappear in old horses. Colonel Poole has seen both grey and bay Kathiawar horses striped when first foaled. I have, also, reason to suspect, from information given me by Mr. W. W. Edwards, that with the English racehorse the spinal stripe is much commoner in the foal than in the full-grown animal. Without here entering on further details, I may state that I have collected cases of leg and shoulder stripes in horses of very different breeds, in various countries from Britain to eastern China, and from Norway in the north to the Malay archipelago in the south. In all parts of the world these stripes occur far oftenest in duns and mouse duns. By the term dun a large range of color is included, from one between brown and black to a close approach to cream color. I am aware that Colonel Hamilton Smith, who has written on this subject, believes that the several breeds of the horse have descended from several aboriginal species, one of which, the dun, was striped, and that the above described appearances are all due to ancient crosses with the dun stock. But I am not at all satisfied with this theory, and should be loath to apply it to breeds so distinct as the heavy Belgian cart horse, Welsh ponies, cobs, the lanky Kathiawar race, etc., inhabiting the most distant parts of the world. Now let us turn to the effects of crossing the several species of the horse genus. Rollin asserts that the common mule from the ass and horse is particularly apt to have bars on its legs. I once saw a mule with its legs so much striped that anyone at first would have thought that it must have been the product of a zebra, and Mr. W. C. Martin, in his excellent treatise on the horse, has given a figure of a similar mule. In 4 colored drawings, which I have seen, of hybrids between the ass and zebra, the legs were much more plainly barred than the rest of the body, and in one of them there was a double shoulder stripe. In Lord Moreton's famous hybrid from a chestnut mare and male quagga, the hybrid, and even the pure offspring subsequently produced from the mare by a black Arabian sire, were much more plainly barred across the legs than is even the pure quagga. Lastly, and this is another most remarkable case, a hybrid has been figured by Dr. Gray, and he informs me that he knows of a second case, from the ass and the Hemianus, and this hybrid, though the ass seldom has stripes on its legs and the Hemianus has none and has not even a shoulder stripe, nevertheless had all 4 legs barred, and had 3 short shoulder stripes, like those on the dun Welsh pony, and even had some zebra-like stripes on the sides of its face. With respect to this last fact, I was so convinced that not even a stripe of color appears from what would commonly be called an accident, that I was led solely from the occurrence of the face stripes on this hybrid from the ass and Hemianus. To ask Colonel Poole whether such face stripes ever occur in the eminently striped Catawar breed of horses, and was, as we have seen, answered in the affirmative. What now are we to say to these several facts? We see several very distinct species of the horse genus becoming, by simple variation, striped on the legs like a zebra, or striped on the shoulders like an ass. In the horse we see this tendency strong whenever a dun tint appears, a tint which approaches to that of the general coloring of the other species of the genus. The appearance of the stripes is not accompanied by any change of form or by any other new character. We see this tendency to become striped most strongly displayed in hybrids from between several of the most distinct species. Now observe the case of the several breeds of pigeons. They are descended from a pigeon, including 2 or 3 subspecies or geographical races, of a bluish color, with certain bars and other marks, and when any breed assumes by simple variation a bluish tint, these bars and other marks invariably reappear, but without any other change of form or character. When the oldest and truest breeds of various colors are crossed, we see a strong tendency for the blue tint and bars and marks to reappear in the mongrels. I have stated that the most probable hypothesis to account for the reappearance of very ancient characters is that there is a tendency in the young of each successive generation to produce the long-lost character, and that this tendency, from unknown causes, sometimes prevails. And we have just seen that in several species of the horse genus the stripes are either plainer or appear more commonly in the young than in the old. Call the breeds of pigeons, some of which have bred true for centuries, species, and how exactly parallel is the case with that of the species of the horse genus? For myself, I venture confidently to look back thousands on thousands of generations, and I see an animal striped like a zebra, but perhaps otherwise very differently constructed, the common parent of our domestic horse, whether or not it be descended from one or more wild stocks, of the ass, the hemionus, quagga, and zebra. He who believes that each equine species was independently created, will, I presume, assert that each species has been created with a tendency to vary, both under nature and under domestication, in this particular manner, so as often to become striped like other species of the genus, and that each has been created with a strong tendency, when crossed with species inhabiting distant quarters of the world, to produce hybrids resembling in their stripes, not their own parents, but other species of the genus. To admit this view is, as it seems to me, to reject a real for an unreal, or at least for an unknown, cause. It makes the works of God a mere mockery and deception. I would almost as soon believe with the old and ignorant cosmogonists that fossil shells had never lived, but had been created in stone so as to mock the shells now living on the seashore. Summary. Our ignorance of the laws of variation is profound. Not in one case out of 100 can we pretend to assign any reason why this or that part differs, more or less, from the same part in the parents. But whenever we have the means of instituting a comparison, the same laws appear to have acted in producing the lesser differences between varieties of the same species, and the greater differences between species of the same genus. The external conditions of life, as climate and food, etc., seem to have induced some slight modifications. Habit in producing constitutional differences, and use in strengthening, and disuse in weakening and diminishing organs, seem to have been more potent in their effects. Homologous parts tend to vary in the same way, and homologous parts tend to cohere. Modifications in hard parts and in external parts sometimes affect softer and internal parts. When one part is largely developed, perhaps it tends to draw nourishment from the adjoining parts, and every part of the structure which can be saved without detriment to the individual will be saved. Changes of structure at an early age will generally affect parts subsequently developed, and there are very many other correlations of growth, the nature of which we are utterly unable to understand. Multiple parts are variable in number and in structure, perhaps arising from such parts not having been closely specialized to any particular function, so that their modifications have not been closely checked by natural selection. It is probably from this same cause that organic beings low in the scale of nature are more variable than those which have their whole organization more specialized, and are higher in the scale. Rudimentary organs, from being useless, will be disregarded by natural selection, and hence probably are variable. Specific characters, that is, the characters which have come to differ since the several species of the same genus branched off from a common parent, are more variable than generic characters, or those which have long been inherited, and have not differed within this same period. In these remarks we have referred to special parts or organs being still variable, because they have recently varied and thus come to differ, but we have also seen in the second chapter that the same principle applies to the whole individual, for in a district where many species of any genus are found, that is, where there has been much former variation and differentiation, or where the manufactory of new specific forms has been actively at work, there, on an average, we now find most varieties or incipient species. Secondary sexual characters are highly variable, and such characters differ much in the species of the same group. Variability in the same parts of the organization has generally been taken advantage of in giving secondary sexual differences to the sexes of the same species, and specific differences to the several species of the same genus. Any part or organ developed to an extraordinary size or in an extraordinary manner, in comparison with the same part or organ in the allied species, must have gone through an extraordinary amount of modification since the genus arose, and thus we can understand why it should often still be variable in a much higher degree than other parts, for variation is a long-continued and slow process, and natural selection will in such cases not as yet have had time to overcome the tendency to further variability and to reversion to a less modified state. But when a species with any extraordinarily developed organ has become the parent of many modified descendants, which on my view must be a very slow process, requiring a long lapse of time, in this case, natural selection may readily have succeeded in giving a fixed character to the organ, in however extraordinary a manner it may be developed. Species inheriting nearly the same constitution from a common parent and exposed to similar influences will naturally tend to present analogous variations, and these same species may occasionally revert to some of the characters of their ancient progenitors. Although new and important modifications may not arise from reversion and analogous variation, such modifications will add to the beautiful and harmonious diversity of nature. Whatever the cause may be of each slight difference in the offspring from their parents, and a cause for each must exist, it is the steady accumulation, through natural selection, of such differences, when beneficial to the individual, that gives rise to all the more important modifications of structure, by which the innumerable beings on the face of this earth are enabled to struggle with each other, and the best adapted to survive.